Okay, welcome everyone to today's Energy Symposium for February 28, 2023. Gary King, Research Scientist and Assistant Director at the Energy Institute. Before I introduce today's speaker, Alex Bump, I will point out the upcoming talks for the next 2 weeks. Well, the third one's 3 weeks from now. So next week, March 7th, we'll have another person from the Bureau of Economic Geology here at the University of Texas, Peter Eichelbold, and he was going to talk about storing hydrogen. So we're going to hear about maybe storing one molecule in the ground, a little bit, CO2, and we're going to talk about storing a different, smaller molecule, hydrogen, next week. And then the week after that, spring break, so no symposium. March 21st, afterwards, we then have Stuart James, who is a research associate in Germany, and they have an open data system. So they have an open online system online for accumulating data about locations of power plants, electric power grids. So it's kind of how do you help do research or help people do research about the energy system by providing open source data on many kinds of important parameters and details that we want to know about. So that will be our talk remote from Germany on March 21st. But today it's a pleasure to introduce Alex Bump. He's a research geologist at the Gulf Coast Carbon Center, which is part of the Bureau of Economic Geology, which is part of the Jackson School of Geosciences, #1 geoscience program in the country, and the University of Texas, one of the best universities in the country. So it's a pleasure to have him here. So he's a geologist there at the GCCC, as we say, so bachelor's in physics and a PhD in structural geology and tectonics from the University of Arizona. Before coming to UT 2019, he had 2 decades in petroleum exploration, including roles as advisor in the discipline for BP, correct? And his current work focuses on reinvention of the well-honed petroleum exploration processes for the challenge of finding and de-risking the geologic storage of carbon dioxide. So we're going to learn about risks and how we go about this. So this is all in the context of climate change and climate mitigation and storing carbon dioxide for all the reasons you might think about. And he's going to put this scale of the challenge of how much carbon storage we can have, and the scale of all the carbon emissions here, 36 gigatons a year. So how does this work, and how are we going to do it safely? We'll now hand over to Alex, and I will switch over your presentation.
Thank you. Not a small challenge, particularly when you put it that way. So let me start by just setting a little context. We hear an awful lot about climate change and about mitigation, right? And the range of voices or opinions on it goes from end of the world as we know it to meh, whatever, right? And the mitigation voices equally wide range, right? Stop doing this, cannot do this anymore, do this right now, right? There's a huge range of stuff. I usually start talks by trying to find a point of emotional engagement. This one, emotions are already high. So I'm actually going to start this by dialing it back, going to look at a bit of context on climate change and on mitigation, see where we start, and then we'll transition into CCS and its role in climate change mitigation. So to start with, I'm a geologist. I tend to take the long view. This is a view of climate and CO2, or temperature and CO2, over part of geologic time, so over the last 450 million years or so. You've got several boxes on here with significant scale changes between them. So the first one runs from 450 million years or so up to it's 55 million years. The second one, D and F, run from 55 million years ago up to just under 1 million years ago. And the last one is the rest up to the present. Top row of boxes is atmospheric CO2 concentration over time. Bottom row is delta F, this is called proxy for temperature. And the point that I want you to take away from this is that these things go up and down, right? Climate and CO2 concentration in the atmosphere fluctuate a lot. Over geologic time, there's been quite a range. And we are now at one of the colder epochs in Earth's climate. Polar ice caps are really rare phenomena in the geologic record. Same polar ice caps we have today. We're at one of the cold epochs. If you look at planetary surface temperatures, you can fairly easily make a calculation, a prediction of what they ought to be based on incoming solar radiation, which is basically a function of distance from the sun, and the amount of reflected energy, albedo as it's called. So those predictions are actually surprisingly accurate for for Mercury and Mars. For Earth and Venus, they're way, way off. And the difference, the reason they're off so badly for Earth and Venus is the greenhouse effect. It's the atmospheric gases that trap incoming solar radiation or trap outgoing infrared radiation. Working? That's fine. Notice the Earth temperature. What we would predict is about minus 15 degrees C, based purely on incoming solar radiation and reflectance. What we actually see is about plus 15 degrees C on a mean annual basis. The greenhouse effect is the difference between a habitable planet and one that would be mighty chilly. That said, as we know, atmospheric CO2 concentrations have gone up and down in the last 800,000 years. And present day, they're well above that, well above the recent past record. The predictions of end of life on Earth and so on are probably overblown. But we live on the Earth as it is today. We built our civilization on the Earth as we see it. And among the very cold, hard-headed assessments of climate change is the US National Director of Security's annual threat assessment. If you open it up, you see the usual suspects, China, Russia, Red, and North Korea. And right down there in the middle is climate change. And what they worry about, if you want to read it, is the destabilizing effects of climate change on humans. So water stress, changing production, changing patterns of agricultural production, crop failures, changed disease patterns, heat waves, floods, sea level rise, all of which stands to destabilize potentially cities, even countries, right? That is the reason that DOD and Director of National Security worry about this stuff. And that brings us to, why do we care? What do we do about it? So there are lots of sources of greenhouse gases. We tend to focus on CO2 because that is the big one. And it's not the only one, but it is by far the majority of the greenhouse effect. And it's by far the majority of our emissions. So CO2 comes from a variety of sources. And I love this particular diagram because it gives you big buckets in the middle. 3/4 of our CO2 production, our emissions, come from energy production and consumption. But if you want a bit more detail, go out on that into the progressively wider circles, and you see how that breaks down. So about 75% in energy, 16% in transport, if you're curious, and about 12% of that is road transport. Energy use in buildings or iron and steel production. There's a lot of different sources here, and we'll think about all of them. So global emissions right now run about 35 gigatons per year from anthropogenic sources. So the graph here is showing you time and horizontal emissions in billions of tons per year on the vertical. And you can see the growing black line, historical emissions. Getting to net zero is a big challenge. And opinions vary about how you do it. This is a fairly middle of the road opinion. They all look fairly similar. About a third of it is gains in efficiency. So things like swapping out incandescent light bulbs for LEDs. About a third of it is different energy sources, wind and solar in particular. Right? So that's 2/3. The remaining third is all other. That all is useful, other bucket. CCUS, which I'll talk about more, is that red wedge. In this view, it's about 9% of the total pollution. Some have it as high as 25%, but it's in that range, around about 10 or 15%, let's call it. So why? 10 or 15% doesn't sound like much. And you hear all kinds of voices about CCS, as you do with everything else about climate change and mitigation. From this is an absolute waste, you should stop doing it now, to this is the solution. It's going to be magic. And of course, there is a middle ground in there, which is effectively what I will argue here. So why CCS? Why do we care about that little 10, 15% wedge? It has a number of roles, and I call it the Swiss Army knife of climate change mitigation for a reason. So role number one, some emissions are really hard to abate. So steel and cement production, petrochemical production has process CO2 emissions. So it consumes energy. You could get the energy from renewable sources, carbon-free sources, but the process of coking for steel production and breakdown of calcium carbonate, limestone, for cement production releases CO2, large volumes of CO2, in fact. Together, those are about 8% of global CO2 emissions. So some emission sources hard to abate. Iron, steel, cement being two of them. Long distance transport. It's going to be hard to put capture equipment on airplanes and trucks, but shipping is an active conversation. There are designs being drawn for carbon capture and storage equipment on ships. Throw it on the ship, store it on the ship, and offload it when you get to port. The other big wedge on this is load following electricity or dispatchable power. So renewables are fantastic, but wind doesn't blow all the time, sun doesn't shine all the time. Night is a thing, right? You still need power at night, and your options are basically either massively overbuild the renewable capacity so that you can milk enough power out of even small volumes of wind, create large-scale energy storage so that you can store it for night, or keep some of the combustible power that we already have in the mix and decarbonize that. If you want to do that, which is the cheap option, CCS. One example of that, Boundary Dam Power Plant. It's a coal-fired power plant in Alberta, and it's capturing 1 million tons a year in sequestration. Another thing for CCS is carbon removal, which we hear more and more about. It's the need to draw carbon out of the atmosphere, start drawing down historical emissions. There's a couple of ways to do it. One is mechanical filtration, like the example you see here, which is from Climeworks in Switzerland. The other way is what we call bioenergy with CCS, BECCS. You grow biomass, harvest it, and biomass, of course, takes carbon out of the atmosphere brilliantly. You harvest it, you burn the biomass for power, and you capture the CO2 at the smokestack. Either way, you're drawing carbon out of the atmosphere, but you got to do something with the carbon. CCS. Two more reasons this is important. And I hate this graph, but it remains the best visual that I have. It comes from an IPCC study looking at the effects of taking various climate change mitigation measures out of the mix. So what if you took out nuclear? Or what if you limited solar and wind? What if you took out CCS? How would that change your approach to getting to net zero, both in terms of cost and in terms of pathways? So the little barrel symbols on this relate to pathways to net zero. If you take out CCS or nuclear or whatever. The percents that you see are the percent change in cost to get to a given level of atmospheric CO2 concentration, or a given level of mitigation. The top row on this is round about 450 parts per million atmospheric CO2 content. The bottom white row is 550. So less mitigation on the bottom. And you can see if you take out nuclear, you change the cost by 7 to 13%. There's a little growth, but you're left with 8 or 10 paths toward net zero. Fine. If you took out solar or wind, it's about the same with an even smaller impact on the cost. If you limited bioenergy, it's a bit more, but similar. CCS is the real swing factor here. Take out CCS and your pathways shrink. They rely on large-scale behavior change and massive reforestation. And the costs more than double. Cost for a given mitigation. So the role of CCS in here is to decarbonize the hard to mitigate stuff, enable the large scale production of low carbon dispatchable power, negative emissions, and economically meet climate targets. In a sense, it's strategic risk management. It gives you lots of pathways. You use it wherever you want, whenever you want, including not at all, but it's a good thing to have in the mix. So how does it work? First, you got to capture the CO2. And in principle, you can do it from any point source. There's a couple of examples here, both from Texas, actually. The one on the left is from Petronova, which is a coal-fired power plant southwest of Houston. And the big circled bit of kit is the capture equipment. These are big, massive pieces of kit. The one on the right is the Air Products steam methane reformer production in Port Arthur, Texas, so southeast of Houston. And again, the circled bits of kit are the capture vessels. Right? These are big things to construct. They're big investments, and they take significant energy to run. What really matters in terms of this sort of kit is how pure is the CO2 stream you're trying to capture. The more dilute it is, the more expensive, the more energy intensive it is. So what really pays for this stuff, first and foremost, is to capture the purest, basically pure CO2 streams. So hydrogen production, ethanol production, ammonia production, and LNG production. The really high volume though is the coal and it's the power plants, coal and natural gas. Even coal is about 14% CO2 in the exhaust stream. Natural gas is about 4%. And if you start thinking direct air capture, that's 430 parts per million. So costs range from almost free, put a funnel over the smokestack, up to something like $1,000 a ton for direct air capture. Once you captured it, separated it from the other gases and compressed it, you got to transport it. Ideally, you keep this as short as possible because transport is expensive, but you've got a few options and they look like all of the usual things you think of. Pipeline, ship, even road or rail. And they all have trade-offs in terms of volume and cost and flexibility. But mostly we're talking about pipelines and to a growing degree ships. The ship there is a drawing from the Northern Lights project, which is offshore Norway. Projects now in construction that aims to use ships to visit Northern European ports, pick up CO2 emissions, and take them to a storage site offshore. And of course, the last component of this, storage. In principle, we have 4 options-ish. You could store it, and this is all deep underground. I'll talk a little bit about how deep in a second. But you could store it in what we call wet reservoirs, saline brines. You could store it in principle in deep, unminable coal seams. You can certainly use it in enhanced oil recovery, so putting it into existing oil reservoirs to sweep oil and to dissolve oil, move it toward producers, which does sequester an awful lot of CO2 in the process. And we can also use it in depleted post-production oil and gas fields. So there's flexibility in how you store. But we'll dig into this because I'm a geologist. I like storage. And because everyone asks about storage. Above ground capture kit, transport kit, fairly easy to understand. It's the storage that people get worried about. So we'll dig into that. And this is a map made by one of our students, Rodriguez, showing potential storage areas around the US. And different shades of blue correspond to different thicknesses of sedimentary geology available for storage. And there's 2 things to take away from this map. One is there's a lot of storage around the US. And it's on the order of thousands of gigatons, billions of tons. We argue about exact numbers, but sufficient for decades, if not centuries, of emissions. The other takeaway is that storage is not evenly distributed. Right? We've got a lot of it on the Gulf Coast, but if you went to the Mountain West, you'd be hard pressed to find anything. Right? Like every other resource, it's unevenly distributed. Same thing is true across the globe. And this is just a map, excuse me, a rather coarse map of sedimentary thickness. Anything in the green and other colors above that on the scale bar is potentially available for storage. Thick enough sedimentary rock. So you can see there's a lot of it around the globe, but that light blue and the white is just too thin. There are potential other storage mechanisms that we could use, but most of that stuff is way offshore and probably not economic. So, point being again, there's a lot of storage around the globe, but unevenly distributed. So, storage. We think of CO2 as a gas at atmospheric conditions, and it is, right? We breathe it, plants take it in, but it's a really compressible gas. And the diagram here just shows its change in density with respect to depth. So as we inject it, or as we go down into the earth, temperature goes up and pressure goes up. Pressure goes up in direct proportion to depth. It's basically, the minimum pressure is basically the weight of a column of water. So just like diving to the bottom of the swimming pool and you feel the pressure in your ears, the reason you feel that is, of course, that you have a tall column of water over your head pushing down on your ears. Same thing is true in the subsurface. We have a column of water that goes either from sea surface offshore or from water table onshore down to wherever we are. So pressure increases linearly and rapidly. And someone online is going to tell me it doesn't increase linearly. That is an approximation, but basically linearly. The result is that CO2 goes from a gas at surface conditions to a supercritical fluid at about 800 meters depth, with a little bit of ish, depending on local temperatures and so on. So this diagram of CO2 volume is trying to show if we want to maximize our use of subsurface pore space, we want to store it supercritically, right? 800 meters or deeper below ground surface. The other big constraint is that we are required by law to safeguard freshwater aquifers and other environmental resources. So in places, we have freshwater aquifers deeper than 800 meters. That pushes the top of our storage window down. So we have to safeguard that. Contrary to popular opinion, there are no big caves in the subsurface. We're not putting this into something that looks like a storage tank on the surface. What you see here is a core sample on the left from a subsurface reservoir, a blow up of that, and then a microscopic view of it. Where we're storing CO2 is in the pore space between sand grains. Right? It's the blue on that thin section on the right-hand image. The blue is epoxy that's holding these grains together on a microscope slide. That's our space for CO2 injection. So when you pick up a sandstone on the side of the road, it looks like it has zero porosity. But sometimes you'll find if you blow into it, you'll find that you can get air in. Put your lips against it, try to push air in. That's showing you porosity, and that's what we're storing CO2 in. It's also what we retrieve oil and gas from. This stuff is well proven. So the thing that everyone worries about is security. What if we put it into the ground? What's going to keep it there? Why doesn't it just come back out? And there's several answers to this. I'll talk more about it. But in broad terms, what happens, we take CO2, we inject it underground into usually a sandstone or carbonate, something with porosity and permeability, like a sponge. We rely on an overlying layer that we call a seal or a confining system with little permeability to keep the CO2 in the ground. The CO2, if it's in water, it's a buoyant fluid, it will tend to rise until it hits something impermeable. And this is the same trapping mechanism we use for oil and gas, right? It is well proven stuff. but that's how we keep it in to first approximation, is trapped in a seal. So you can see it here in the cartoon pulling against a high, right, with the overlying seal. It's risen uphill, pulled against that high. So number one, the seal limits the buoyant rise of CO2. But if you look at the grain scale, we see something else, and it's called capillary trapping. And in fact, there's two mechanisms. There's dissolution, putting CO2 into water, and there's also capillary trapping. So as CO2 flows through sand grains and flows through these narrow little constrictions in the pore throats, you leave little bubbles of it behind. So the easiest way to explain this is by analogy. You think of going to the beach, nice day, and for whatever reason, you spill your drink, right? It soaks into the sand, and you really wish you could get it back. But you cannot pick up the sand grains and bring your drink back out, right? A lot of it stays there, wetting the sand grains. The same thing is true in the subsurface. And Sue will always point out that this isn't perfectly analogous. Her favorite analogy would be the grease spot on your shirt. Go out to lunch, you have a nice lunch, and of course you spill a little bit of food on your shirt with the grease spot. And you cannot take the napkin and just wipe it off. You need soap. It's the same phenomenon. It's fluids, what we call non-wetting phase fluids, getting trapped in the between the pore throats. So the more sandstone pore throats we flow CO2 through, the more of it we residually trap, and it's irretrievable without things like soap, secondary recovery, as we call it. So let me give you a couple of examples, or one example of what this looks like. This is Sleipner. It's a North Sea oil production platform that produces gas from a high CO2 gas field. Norway has a high tax on offshore CO2 emissions and a phase tax on CO2 emissions, such that it really pays, even in 1996 when this started, to capture the CO2, separate it, and re-inject it, rather than paying the tax. So Sleipner has been capturing and sequestering about 1 million tons a year since 1996. The way it works, cross-section view, you see the sea at the top and the production platform. They produce gas in a deep reservoir. They separate it on the platform. Gas goes to shore, CO2 gets compressed and re-injected in shallower aquifer called the Utsira formation. And you can see the little CO2 plumes schematically expanding above the well on this with a confining zone above it. We can actually look at this. So what's really cool, I love seismic images, but for those unfamiliar, seismic is our really fundamental tool for looking at what's underground. It's basically a sonograph here. It's echoes. It's using sound sources to put acoustic energy into the earth and listening to the echoes. And the images that you see here, the top row of images are cross sections from repeat seismic surveys. And the bright amplitude blooms, the blue and red that you see changing between images, that is the signature of CO2 in the subsurface. So CO2 plus water reflects sound differently than just water. The layering that you see in those images is rock layering. The one on the left is from 1994. Then you get 2001, 2004, 2006, 2008. We can watch the CO2 plume expanding in the ground. The ones on the bottom, the blue images, are map views, same seismic. You can see the CO2 plume expanding, doing exactly what we would predict it does. Now, the thing everyone worries about, as I said, is, basically it comes from unfamiliarity, but it's all of the catastrophes that you could imagine underground. It's escape of CO2 or contamination of groundwater or earthquakes, right? So the cartoon here shows you an atmospheric CO2 source, and we can substitute atmospheric release for underground injection. We fill the buoyant trap, that concave downward geometry that you see. But the risks, what are the risks? It could escape up a fault in principle. It could come back up the outside of the wellbore we're injecting through, or another abandoned wellbore, or potentially a long tortuous lateral escape path, something that we haven't thought of. And of course, there's the risk of earthquake. So what do we do about this? How do we assure investors and regulators and public this is actually safe? And there are a whole bunch of answers to this. First and foremost, Mother Nature has been doing this for geologic time. We know of lots of naturally occurring CO2 accumulations that are absolutely secure. I have drilled 2 of them in the course of petroleum exploration. Thought they were going to be oil, not so much, but it's CO2 in industrial volumes that's been there for 70, 80 million years, right? Mother Nature can store this stuff for geologic time, just as Mother Nature stores oil and gas. Second answer, we have actually been doing this as humans and as an industry safely and effectively for a good 50 years. And it starts with CO2 enhanced oil recovery in West Texas, 1972. Injecting CO2, naturally occurring CO2, in fact, into the ground to help with oil recovery. It works, and we've developed a lot of experience in handling and injecting subsurface storage of CO2. Commercial scale CO2 sequestration goes back to 1996 and Sleipner. And there are a lot of pilot and academic research projects, largely in the US, but actually represented around the world, some of which have been done. Many of the pioneering ones have been done by my colleagues at the Carbon Center. So, Mother Nature, human experience. There are a lot of CO2 projects. As I said, this is a map of historical and current ones from 2 years ago. Various colors, but take it that each dot is a CO2 injection experiment or project, commercial scale project. There's a lot of them. I'll come back to this in a second. But as we transition from injection of CO2 for enhanced oil recovery to commercial scale or climate change mitigation scale, CO2 sequestration, we start rethinking what we know about subsurface trapping. So many of us come to this from oil and gas, and even those who don't come from oil and gas are heavily informed by oil and gas, because oil and gas, buoyant fluids, trapped in the subsurface for geologic time, they're decent analogs, and we have a lot of experience with this. So if you look at a cross-section of the subsurface, and keep the scale in mind, that's 4 kilometers on the vertical. I traced this off a seismic line, so I'm not making this up. You have a salt body in pink, and you have a bunch of sand layers in yellow with intervening muds, impermeable seals in the gray. Where we would expect to find gas or oil is up on the top, the crustal positions on those sand layers. So buoyant fluids rise until they can rise alone. And you see the red intervals on this are hypothetical gas accumulations, really typical of Gulf Coast. And we get a bunch of wells that happen. Again, typical of Gulf Coast. You could use the same reservoirs, the same traps for CO2 storage, and it would work. But the difference between oil and gas and CO2 is that oil and gas is valuable and we want to produce it. We want to get it out of the ground. So we look for the concentrated mobile accumulations, places where we can stick a well in and get a lot out. Our goal with CO2 is to get rid of it. It's permanent sequestration. So we are not bound to those structural buoyant traps at the crest of a structure where it will stay mobile and concentrated. We would much rather inject it down on the flank of these structures and allow it to migrate up. So contact pores with unsaturated water in them, where you can dissolve a bit of CO2, pass through lots of pore throats where you residually trap a little bit of CO2 on every pore throat, and encounter whatever little buoyant traps you can on the way uphill. So those buoyant traps could be things like the little faults that you see on here. but they can be as small as just undulations on the top of a flow unit, right? Think of this somewhat like pouring your drink on the sidewalk on the hill, right? Every little crack in the sidewalk soaks up a bit of that drink. And if you pour it on the grass beside the sidewalk, lots of heterogeneity, lots of rugosity, it doesn't flow anywhere at all. It soaks in right there. Good choice of injection horizon can do the same thing. So lots of people look at this and say, yeah, interesting idea, but it's going straight up the hill, right? It's going to migrate up the crust, which oil and gas does, but we put in huge volumes of oil and gas. Good source rocks generate on the order of 10 to 100 million barrels of petroleum per square kilometer. It's enormous volumes. The volumes of CO2 we're putting in the ground are vastly less. So it's just like pouring a drink on the sidewalk. Small drink, you might be on a steep hill, but it doesn't go very far. I introduce this to illustrate the point. I'm going to draw on the thesis work from another one of our students, Naliana Olfley. And this is a seismic line through her thesis area offshore Houston. And what you see, lots of stripiness. Those stripes are rock layers. So you can see some structure to them. They're low on the left. They rise up toward an anticline, as we call it, or a fold, a buoyant trap on the right. And her thesis was about what happens if you inject down on the flank of this structure. How much CO2 could you expect to arrest as it migrates uphill? So she's done lots of characterization work, lots of careful modeling, and I'm going to skip right through all that and show you the result. So there's 2 experiments here and 2 times. You see the same cross-section. The one on the left has 60 megatons injected. The one on the right has 30 megatons. And both of them inject at the white rectangle down on the flank. Top row shows you CO2 distribution at the end of injection, and the bottom row shows it 100 years post-injection. Bit of equilibration. But the point of this is, even 100 years post-injection with 60 megatons injected, CO2 flows uphill, but not very far. Right? It barely gets to the crest, let alone all going there and cooling there. You can do things with CO2 that we don't consider possible with oil and gas. And it's because of different goals, basically. So why don't you see more of it? Why aren't we doing this at scale right now? There are 3 barriers. None of them are in the subsurface. None of them are technical. So barrier 1 has been legal framework. And there's a whole bunch of legal questions here that will seem kind of obvious, but get in the way of actually doing this. So how do you classify CO2? Is it a hazardous waste that requires special handling, or is it just waste? Right? What are the legal requirements for permitting a storage site, monitoring it, demonstration that it's secure? Is there a permitting process in place? Is there provision for crossing borders with CO2? Right? What defines a storage site? Who owns the pore space? Here in Texas, is it the mineral owner who owns the contents of pore space, or is it the surface owner? Legal opinion is that the surface owner owns it, but it's taken a while to settle that question. Provisions for eminent domain and long-term liability. All of these things get in the way, and they're changing. UN framework convention on climate change, London Protocol, ISO, and various country-specific laws. You see there's a whole suite of them passed around the late 2000s, 2010. Such that the map of legal maturity for CCS today, there are some countries that are absolutely ready for it, many countries that are on that journey, and some that haven't started. Like everything new, be it oil and gas or be it cryptocurrency, regulations evolve, and you need those regulations to facilitate an industry. Second barrier is the business model. The first carbon pricing schemes came into existence in the early 90s. This graph shows you a handful of them from 2008. And great that they're there, but the price for storing carbon or taking carbon out of the atmosphere is not much. It's been, in general, cheaper to pay the taxes or the penalties. That is rapidly changing. So if I take off the mask over the last bit of this graph, you see the red line is the European Union carbon price. It hit 100 euros per ton for the first time last week. This is incentivizing serious movement. If you look at the countries with carbon pricing schemes, it's actually a fair representation of the industrialized world now. Again, changing fast. So this graph gives you some view of how much it's changing. Time on the horizontal, each nation is one bar, one color on those bars, and vertical is share of the world's greenhouse gas emissions that's covered. So you see it starts in 1990 with Poland and Finland, the pioneers. But look at the growth over time. Not much until 2005. And then fairly steady growth. And in the last 2 years, the addition of China, which is the light blue bars on this. Now about 25% of the world's CO2 emissions are covered by carbon pricing. You will notice the US is conspicuously absent. The US does not have a nationwide carbon tax or emissions trading scheme. Instead, what we have, and this is the art of the politically possible, what we have is a tax credit for sequestering carbon. It's called 45Q. And up until 2019, it was $10 a ton. 2019, that changed to $50 a ton. And it was enough to spark significant action. Last year, with the passage of the bipartisan infrastructure law, that changed from $50 to $85 a ton, with a number of other changes that make it a much more investable proposition. So right now, from any point source, the US tax credit is $85 a ton, and the tax credits are now tradable. If you get it from direct air capture, it's $180. And this is incentivizing all kinds of movement. So the global capture and storage capacity, we see over time, there was a spike of interest around 2010, 2011. It waned significantly in the teens and is coming back with a vengeance. This is forecast to almost double next year, given the number of projects announced. And in all seriousness, there's talk of it being gigaton scale within a couple of decades. Which brings me to barrier number 3, and it's public acceptance. So 2 photos here. The one on the left is Germany in 2011. And for those who don't speak German, the sign is Heimbom CO2 storage site. Right? There's been a lot of concern that CCS is either greenwashing or in some way a Superfund site that is going to come back to bite us. The one on the right is Louisiana, just last year. And Livingston Parish, residents who are unfamiliar with CO2, CCS, and can blame them, they got really, really concerned about 2 announced storage projects that were beginning characterization in their parish and put a year-long moratorium on development. Ostensibly to understand it, but really to get comfortable with this or not. It's an open question. So balance that against all of the social pressure for action on climate change. And who knows exactly where this is going to go. But I keep having to update this slide because the number of net zero pledges is changing all the time. Climate mitigation is climbing the radar across the world. And in round numbers, about 90% of the world's emissions, GDP, and population is now covered by some sort of net zero pledge. And I stress the some sort. It's ranged from highly credible to aspiration. But contrast this with even 5 years ago, let alone 10 years ago. It is progress. So how do you forecast growth? And this comes from another one of my colleagues from Tipnickel, who simply took historic oil industry growth curves from Gulf of Mexico, onshore Texas, offshore Gulf of Mexico, and offshore Norway, and said, what if you reproduce these same growth curves in terms of number of wells and in terms of volume with CO2? So red on this is Norway, orange is offshore Gulf of Mexico, and blue is offshore Texas. And if you simply replicated the number of wells with average CO2 wells, what you can see is that you get to gigaton scale within a couple of decades, a decade. So I'll wrap this up with one analog. Transitions are hard, right? But we can look back and see lots of historic transitions and analogs for this kind of thing. So those of you who spent time in New York City or London or Paris, you know, the older neighborhoods have these beautiful elevated front steps, right? Steps leading up to an elevated front door. And they look great today. But there's a historical reason for those. When they were built, late 1800s, oftentimes, those cities were full of horses. New York had 100,000 horses, producing 2.5 million pounds of manure a day. Streets were absolute cesspools, and there's a reason that everyone means flood the city in the summer. The world's first international urban planning conference was held in London in 1894 to deal with what was termed the manure crisis. Right? And there were dire predictions that in 50 years, every street in London would be under 9 feet of manure. Manure would reach the second story windows of New York. They had a week for this conference, and it gave up after 3 days. Went home because the problem was unsolvable. Of course, it wasn't. Transition from horse to car transformed cities and arguably sowed the roots of today's problem. But there's two things to take away from this. One, these problems are solvable. Number two, it's not a question of no impact. It's a question of what impacts can we work with. And I'll skip the discussion of acid rain and finish by saying that all technologies, all pollution mitigation technologies follow the same sort of curve. They go from science fiction when they are first conceived to doable but prohibitively expensive, province of university research. But with R&D, a bit of trial and error, they get to the point where they make sense in certain circumstances. And that's where we are with CCS today. The last phase on this is routine deployment. And I think we can see it on the horizon. So with that, thank you all for your attention, and thank you to the sponsors of the Gulf Coast Carbon Center.
All right, give them a call. A couple online. Anybody in the room with a question so far? Yeah.
My question is, why is like direct air capture more incentivized as compared to other carbon capture methods, such as biochars, which is going to be more or less expensive than that methods?
Yeah, fair question. I think it comes down to politics. Direct air capture is expensive, so if you're going to do it, you have to incentivize it. But there is also significant pressure, and pressure from particularly the greenest of the green lobby for direct air capture.
Why is there no methods to why is the green lobby is not seeing a value for biochar?
I think they very much do. I actually couldn't tell you how biochar figures into this. But sequestration, by any means is useful. The difference really is about time frame and permanence. Biochar, great, but what happens when it decomposes? How long are we locking up CO2? And the same is true of trees and biomass. You can sequester a lot of trees in a forest, and it can go up in an instant in a forest fire. Subsurface sequestration is permanent. It's geologic time.
Here's a question online related to an early slide about your picture of direct air capture. It was in, it said, I guess, in Switzerland and the green field around it. This is maybe not exactly your area, but the question is, does anybody expect any surrounding effect from direct air capture due to lowering the CO2 locally? I guess it's got to be a very small percentage
Good question.
local, but I don't know the numbers, but
As far as I know, no. The atmosphere mixes too easily, it homogenizes too easily. This is, part of one very small part of a very large scale effort to draw down atmospheric CO2.
else in the room. A couple of questions online, perhaps I might phrase them at the same time. One you've somewhat addressed, just asking about the scalability and cost of CCS. So anything more you want to say on that? Also the follow-on question of who's responsible for paying for it. I suppose technically all of us, one way or the other. But and that dovetails to one of your last slides, one of the last few where you showed typicals projection curves. So there's just questions on that with regard to the Texas curve. Is it onshore, offshore, and this kind of thing? So these things are all about scalability and costs and what I expect in the future.
Yeah, so fair question. It is thoroughly scalable. It's really a question of will and incentive. So those curves that I showed you are historical curves. The Texas one is onshore Texas. So that particular one has a significant component of figuring out how to do oil and gas. It's early 1900s. The orange one was offshore Norway. Or red one, I can't remember. That was a much more technologically mature industry, something more analogous to what we see today. And you can see the curve grows faster. Technically, we can do CCS. We have done for 50 years. We can scale it. It's a question of the above ground factors and how quickly those mature.
Right. Well, I guess the main difference is CCS in the past is injecting fluid and taking fluid out, so the pressure doesn't build. And now the idea is keep injecting CO2 and the pressure builds differently. I don't know how significant that difference is. I mean, it sounds significant to me as a non-geologist.
Yeah.
How do I understand that?
Fair question. And this is where we do a lot of research. Injection, if you don't balance it with withdrawal, is going to increase subsurface pressure. We do it today with saltwater disposal at gigaton scale, saltwater produced in the course of petroleum production. We're proposing to do it with CCS. We know very well what subsurface pressure looks like and what the safe limits are. It's the sort of thing that we can do, but we need to keep a very close eye on.
Right.
So,
do you expect something similar? So I know obviously the Texas, Oklahoma, there were, Sue's listening, she'll get mad if I ask this, but I ask in a nice way. People talk about seismicity issues with injection, and it happens with hazardous wastewater from hydraulic fracturing. And then, in Texas at least, we built a seismic network. Bureau helps monitor to track these kinds of things. I suppose we can imagine a similar type of thing for CCS, right?
the
Monitoring network.
Absolutely. So part of the requirement, the statutory requirement for this is monitoring. And part of my job as geologist is assuring site safety, including the risk of induced seismicity. The one thing I will add here that may be a bit more reassuring than just leaving it to me as my job is that the regulations for saltwater disposal were written in the mid-70s. Those are part of the Clean Water Act, 1974. The regulations for CCS also stem from that underground injection control program, but they were written in 2010. So with the benefit of a great deal more experience, and they are by far the most stringent regulations under the underground injection control program, including regulations about maximum pressure and risk of induced seismicity. So they benefit from hindsight and experience.
Room. All right, so we'll go online again. Do you have any idea about the viability of projects based upon the size, or quantity injected per year, and how that might play out on any kind of scenario, offshore or onshore Texas, or is it just kind of a matter of the incentives that we've stated with 45Q, or do you have any insight into the size of existing projects and how we might expect them to pick up?
Good question. So the two biggest projects now operating are Gorgon on the northwest shelf of Australia and Lula offshore Brazil. And those are 5 and 8 megatons per year, respectively. So many of the announced projects along the Gulf Coast and other parts of the world are on that order, 5 to 8 megatons per year. That, is the current going scale. Ultimate sequestration of on the order of 100 million tons each. I see no reason to doubt it.
So I'll try not to do math in my head too fast. So let's say we have 10, you think 10 million tons a year is a viable project size, or 100?
10 million tons a year is a viable project size. Given lots of other geologic assurance.
10% of 35 tons, gigatons of emissions, that's 3,000 million tons. So is that 300? That's not, 300 or 1,000, or the hundreds of thousands of projects, which is maybe not, it's not ridiculous, it's not a million. Well, we have millions of oil and gas wells. So
we have 1.1 million oil and gas wells in the Gulf Coast alone. We can scale this, and the numbers work.
Right. Let's see. I'll read this other question here. I'll just read the question to stating so you can address it. We have a large leap of faith that all these CO2 will remain underground. We come from oil and gas, understand gas leaks, and we measure headspace gas for understanding migration and all these kinds of things. So how are we so optimistic about CCUS, or are we just leaving the problem for the next generation? Maybe this is just a skeptical argument against your confidence of tracking CO2.
Fair enough. I'll give you a couple of anecdotes about this, and take these on top of the natural accumulations and the proof that we can hold it for geologic time. Anecdote number 1 comes from Sue Lorca and her experience with the Frio pilot project, where she injected several thousand tons of CO2 down a well into the subsurface, came back 2 weeks later and tried to get it back out through the same well. And she tells this better than I do, but picture a good Louisiana oilman swabbing this well and trying to pull CO2 out of it, and finally turning to her and going, "Lady, this here well ain't no good, I'm sorry." Couldn't get it back out, right? Residually trapped and dissolved. Anecdote number 2 comes from another colleague, Catherine Romanek, who did a major groundwater study above the Sac Rock field in West Texas, where they've injected, at the time, 80 million tons of CO2. And they've got thousands of old wells in this field. She was absolutely certain that in sampling groundwater, she could pick up traces of contamination with modern laboratory techniques. Took over 100 samples of groundwater and threw every analytical technique she could at it. Found absolutely nothing. Most disappointing, boring result ever, but promising for CCS. So to answer your question, fair to be skeptical. And absolutely approach it that way. But our experience from geology and from doing this ourselves is that we can do this safely at that scale.
You make sound, being a geologist, studying this exciting to create an experiment so that when you do a sample, you get no measurement and you get excited about having nothing and no signal in your measurement. Okay. Well, I think we'll end there. Let's thank again Alex Bump, research geologist from the Gulf Coast Carbon Center here at UT Austin. Thank you very much.
Thank you for having me.